Hey everybody, new lecture. I guess this is lecture 12 of pre-calculus algebra. And I think this is going to be another quick study, just like our last lecture was a quick study. We're going to talk about a library or a repertoire of functions. And just to give you an example, if we were to study chemistry, there would be some chemical compounds that we would be expected to know by name and by symbol. For example, if we saw that chemical compound, we shouldn't have to look it up in a book to know that it's water. And there are other chemical compounds that we encounter frequently, phosphoric acid, carbonic acid, so forth and so on, that we should know the chemical formulas for. We shouldn't have to look them up. We encounter them so often that we just need to know them by sight. And the same is true with the graphs of some basic functions. There are about 6 or 8 functions whose graphs that we should know. When we see the graph, we should know what the function is. When we see the function defined, we should know what the graph is. So let's just start at the beginning here. Our book calls this the identity function, f of x equals x. It's the same as y equals x. And our book calls it the identity function, I guess, because we put a number in and we get that same number back out. But we should know the graph of this function. And remember again, y and f of x are the same thing. So we should look at this and say, you know what? This is the same as y equals 1 times x plus 0. And that means it's in slope-intercept form. Slope is 1, and y-intercept is 0. If the y-intercept is 0, then it crosses the y-axis at the point 0, 0. And if it has slope 1, that means that from this point we go over 1 and we go up 1 to get another point on the graph. So the identity function is the function whose graph is such that the x-coordinate and the y-coordinate of every point on the graph are the same. So the graph of f of x equals x is just a line that goes through the origin and has slope 1. Know this function. And just as an easy way to remember it, we'll know 2 points on the function, okay? We'll know the point 0, 0, and the point x equals 1, y equals 1. This is our identity function. learn to recognize this thing by sight, and learn to recognize that given f of x equals x or y equals x, this is what the function looks like. We want to have that memorized. Now let's go to the next function on our library. The next function in our library is the constant function. F of x equals some constant b. And that's the same as y equals some constant b. So here's the key. We find this point B on the y-axis. Here it is, B. And realize that no matter what x is, f of x is b. Y is equal to b regardless of what x is. So if we go out here to x equal 2, f of x is still b. This is the set of all points where y equals b. And that's just a horizontal line. So for the constant function, learn this. It's the horizontal line that goes through the point B. And as an example, f of x equals 3. Let's just see what this baby looks like. Here's our constant. So right here where y equals 3, that horizontal line passes through the y-axis. Here's the graph of f of x equal 3. In general, know the graph of this function. F of x equals a constant b. It's just a horizontal line going through the point B on the y-axis. What do we have next? Oh, good. Something a little bit more interesting, the square function. Next on our list is the square function. F of x equals x squared. And to plot this graph, let's just use 3 key values of x. We should have this graph memorized, but I want to plot the graph also because when we do variations of the graph, the approach that we're about to use here will make graphing very easy. I'm going to take x values, -1, +1, and 0, and I'm going to take these 3 values of x and plug them into the function to get my x squared. If I take -1 and put it in here for x, I'm going to get -1 squared, which is +1. So when x is -1, f of x, the y value, is +1. So 1, 1 is a point on this graph. Now I'm going to use 0 as an x value to plug into this function. If I plug in 0 for x, I'm going to get 0 squared, which is 0. So when x is 0, f of x, the y value is 0 also. So x is 0, y is 0 is a point on this graph. So there's my second point. And then as a third point to plug in here, I'm going to take +1. F of +1, I take 1 and I substitute it for x, so I'm going to get 1 squared, which is 1. When x is 1, f of x, or the y value, is 1. So the point 1, 1 is on the graph also. And now I just play connect the dots. And this is what my graph looks like, the squaring graph, or the square graph. Learn to recognize this graph by its appearance, and learn that when we see this equation, f of x equals x squared, this is what the graph looks like. This is going to be part of our repertoire. And also remember how we plotted this graph. We chose the points x equal -1, x equals 0, and x equal +1. We're going to use that approach when we do variations of this graph in the next chapter. Oh, if you thought that last example was hard, this is going to be a real killer. The cube function, f of x equals x cubed. We want to be able to know what the graph of this function looks like. And when we see the graph of this function, we also want to know that the graph represents f of x equal x cubed. Our approach to graphing this is going to be exactly like our approach for x squared. We're going to take 3 key x values and plug them in. And then we're going to plot the graph of the function. So we take 3 key x values, -1, 0, and 1, and we'll plug each of these in. If we plug in -1 for x, we'll get f evaluated at -1. And to get this y value, we take -1 and substitute it in for x. So we get -1 cubed. And let's see. -1 times -1 is +1. Times -1 again is -1. So when x is -1, f, the y value, is also -1. So this point, -1, -1, is on the graph of the cubing function. Yep, I just barely did get that in the field of vision. Okay, let's do the same thing for x equals 0. When we substitute in 0 for x, we get f evaluated at 0. And we substitute 0 in for x, we get 0 cubed, which is 0. So when x is 0, f evaluated at 0, the y coordinate is 0 also. So 0, 0 is a point on the graph of this function. And I think maybe I'll write it up here to keep it out of the way. Well, we got 2 points on the graph. Let's take 1 and substitute it in for x. I have f evaluated at 1. So every place up here in my model that I see an x, I'm going to put 1. So I have 1 cubed, that's just 1. So when x is 1, f evaluated at 1, the y coordinate is going to be 1 also. So here's a third point on our graph. And we play connect the dots. And voila, we have the graph of the function. Memorize this graph of the cube function. Also, remember how we got this graph because we're going to use the same technique to get variations of this graph in the next chapter. Remember the three key values of x that we picked: -1, 0, +1. We let those three values show us what the graph of f of x equal x cubed looks like. Function. What do we call this thing? The square root function. Okay. F of x equals square root of x. And we're going to do pretty much the same thing we've done already. We're going to take a couple of vanilla values of x and plug them in to get the y values. And we try to evaluate f at -1, and we get the square root of -1. And that doesn't correspond to a real number. As a matter of fact, none of these values to the left of the y-axis, none of these values which are negative, are going to give us a real value of our function f. So there ain't no point on the graph that corresponds to f of -1. There ain't no point on the graph that corresponds to f evaluated at -2 and so forth. So x equal -1 didn't work, but we still have our two favorites, 0 and 1, to plug in. So we'll take f evaluated at 0, and that's the square root of 0. Let's see. What number do we have to compute the square root of to get 0? What number times itself is 0? Oh, I know. 0. F evaluated at 0 is 0. So in other words, when x is 0, y is 0. So this is a point on the graph: 0, 0. Now we try the same thing with one of our favorites, x equal 1. And we evaluate f at 1. And we have the square root of 1. Well, let's see now. What number do we multiply by itself to get 1? Oh, I know. 1. When x is 1, f evaluated at 1 is 1. When x is 1, y is 1. So x equal 1, y equal 1 is a point on the graph. Now I have 2 points here. And if the graph of this function is a line, I'm fine. I use these 2 points and zip, zip, I draw my line. But what if the graph of this function isn't a line? I think we need another point. None of these values to the left of the y-axis work because they're negative. And if we put a negative under the square root sign, we don't get a real number. So I'm going to take a number to the right of the y-axis. And since I have to put it in this square root or under this square root, I'm going to take a number whose square root I know. I know the square root of 4. It's 2, so I'll use that as my third value to plug in. F of 4, f evaluated at 4 is the square root of 4, which is 2. So when x is 4, y is 2, and bravo, whoops, I have my graph. And this is what the square root function looks like. Remember how we got it. Remember we tried the magic points -1, 0, and 1, and -1 didn't work. So we stayed with 0 and 1 and took a number whose square root we knew, 4. Remember what this graph looks like, and remember how we got it, because we're going to use this technique in the next chapter to make variations of the square root function. Next on our agenda, the cube root function. Well, we try 3 magic points again. Let's go with -1. And we evaluate f at -1. And we get the cube root of -1. And you know what? That works. The cube root of -1 is the number that we multiply by itself 3 times to get -1. Now, what number is that? Let's see. Maybe -1? Let's see. -1 times -1 is +1. Times -1 again is -1. Yep. The cube root of -1 is -1. So we're going to plot that point. And we have the point -1, -1 on our graph. And you know what? I think I want to put it down here. -1, -1. There we go. Now let's try x equals 0. That usually works. F evaluated at 0 is the cube root of 0. And the cube root of 0 is the number that we multiply by itself 3 times to get 0. And I think that's 0. Let's check. 0 times 0 is 0. Times 0 again is 0. 0 is the cube root of 0. So when x is 0, f of 0, the y coordinate is also 0. So here's a point on our graph. And we'll try 1, x equal 1. That always works. We have the cube root of 1. Let's see. What number do we multiply by itself 3 times to get 1? It's 1, right? 1 times 1 is 1. Times 1 again is 1. Yeah. The cube root of 1 is 1. So when x equals 1, y equal f evaluated at 1 is also 1. So this point 1, 1 is on the graph. Now, I have somewhat of a dilemma because it looks like the graph of this function could be a line, but maybe that's a coincidence. I want to pick one more point, one more value to plug in, and it has to be a number whose cube root I know. I don't know the cube roots of 2, 3, 4, 5, 6, and 7, but I do know the cube root of 8. The cube root of 8 is 2. 2 is the number that we multiply by itself 3 times to get 8. 2 times 2 is 4. Times 2 again is 8. Yep. So 2 is the number that we multiply by itself 3 times to get 8. So that tells us that the cube root of 8 is 2. When x is 8, y equal f evaluated at 8 is 2. So the point x equal 8 and y equal 2 is on this graph. And now clearly I can see that my graph is not a straight line because this point is not going to be on that line. So I'm going to have to go through this point And I'll get something like that. And on the other side of the y-axis, the same kind of thing is going to happen. So this is the graph of f of x equals cube root of x. Memorize it, know what it looks like. Next candidate, the reciprocal function, 1 over x. And we'll take negative 1, that always seems to be a good point to use. X equals negative 1. So we'll have f evaluated at negative 1. And that's equal to 1 over negative 1, which is negative 1. So when x is negative 1, y equal f of negative 1 is negative 1. So x is negative 1, and y is negative 1, okay? Now the next point that we want to try is 0, but oh, look what happens when we try 0. Whoops, undefined. So apparently at x equals 0, there's no point on this graph. Okay. Well, let's try another point. We usually try x equal 1. Let's try that. F of 1 is 1 over 1, which is 1. So when x is 1, y equal f evaluated at 1 is 1. Okay, there's a point on our graph. And initially we may be tempted to connect these two things, but we remember that x equals 0, this function's not defined. So there's no point on the graph right here at the origin. So the graph of this function is not a line that goes through these 2 points. We're going to have to investigate further. Oh, let's take 2. If I let x equal 2, then I get 1 over 2. So let's say, when x equals 2, y equals f evaluated at 2, which is 1/2. Okay. Well, not knowing what else to do, I'll try f of 1/2. And I'll get 1 over 1/2. Now think about this. I'm dividing by a fraction, right? And when I divide by a fraction, isn't that the same thing as taking the numerator and multiplying by the reciprocal? So I'm going to get 2. When x is 1/2, y equals f evaluated at 1/2, which is 2. So, okay, 1/2, 2. And this point is 2 1/2. And I got the picture. I see what's going on. I get it. It's going to look something like this. And the same kind of thing is going to happen to the left of the y-axis. This is the graph of the reciprocal function. If we want to make it a little bit easier to remember, that we can remember these 2 points, 1, 1, and -1, -1, and just know that the graph does this sort of thing. This is the graph of the reciprocal function. Memorize it. But we want to memorize the appearance of all of these functions because we're going to look at variations of the functions. And having a repertoire of these basic functions will make it easy for us to do the graphs of functions that are simple variations of these basic functions. And we got one more function to look at. Here's our last basic function, absolute value of x. And to do this, we take the 3x values that we started with and just substitute them in for x. We'll start with f evaluated at -1. That's the absolute value of -1, which is +1. So when x equals -1, y equals f evaluated at -1, which is +1. So -1, +1 is a point on the graph. Now we'll try our old friend 0, and we'll substitute that in for x. F evaluated at 0. Every place we see an x in our definition, we put a 0 down here. So we have the absolute value of 0, which is 0. So when x is 0, y equals f evaluated at 0, which is 0. 0, 0, okay. And one more point. When x is 1, we have the absolute value of 1, which is 1. So when x is 1, the y value, f evaluated at 1, is equal to 1. And unlike the square function, this graph is made up of 2 straight lines. So we have a straight line to the left of the y-axis and a straight line to the right of the y-axis. And this is what the square root function looks like. This is the last of our repertoire of functions. Memorize the graph of this function. Now there's one other thing that we have to look at in this lecture, and it's something that's called a piecewise function. Here we go, piecewise functions. I don't think our author actually defines what a piecewise function is, so I'll define it. A piecewise function is a function whose definition changes at some point in the domain. And here's the classic example. We kind of sort of know what the absolute value of x is. Here's the definition. It's a piecewise function, which means that at some point in the domain, the definition of this function changes. And the point in the domain where the definition changes is x equal 0. If If x is less than 0, then the absolute value of x equals negative x. That's how we define it. For x greater than or equal to 0, the absolute value of x is positive x. So right at x equals 0, the definition of absolute value of x changes from negative x, which is how we define absolute value of x if x is is less than 0, to positive x, which is how we define absolute value of x if x is greater than 0. And let's work with this for a little bit. First, let's draw the graph. And remember, the point in the domain where the definition changes is x equals 0. Now, what do we know about the set of points in the xy plane where x is 0? Isn't the equation x equals 0 another name for the y-axis? So here's our y-axis, and that's exactly the same as saying that x equals 0, because the y-axis is the set of all points in the xy plane where x equals 0. So to the left of x equals 0, where x is negative, we define the absolute value of x this way. To the right of the y-axis, where x is positive, we define the absolute value of x this way. So let's see. Let's look at the first definition. F of x equals negative x. Isn't that the same as f of x equals negative 1x plus 0? This is the equation of a line in slope-intercept form, where the slope is negative 1 and the y-intercept is 0. So we have a y-intercept at 0, and the slope is negative 1. So let's see, n is negative 1, and that's the same as 1 divided by negative 1. So I can say if I go negative 1 units in the x direction and positive 1 units in the y direction, I'll get another point on the line. That's it. So that's how I get the graph of absolute value of x to the left of the y-axis where x is negative. And you know what? I should have left this point open because this definition only works for x less than 0. And right here at this point, x is equal to 0. So I guess we'll have to use this part of the definition to see what the rest of the graph looks like. This part of the function, where x is greater than 0, is f of x equals x. But isn't that the same as saying that f of x equals 1 times x plus 0? This is the equation of a line in slope-intercept form where the slope is 1 and the y-intercept is 0. And this time, our definition applies when x equals 0. So let's see, when x equals 0, f of 0 equals 0. Okay. So we can fill that point back in. 0, 0 is a point on the line. And for the rest of the x values where x is positive, the graph of the function is just a graph of a line with slope 1 and y-intercept 0. So slope 1, I can write that as 1 over 1, which means that if I go 1 unit in the positive direction, and then I go up 1 unit, I get a point on the line. So positive 1 unit in the x direction, positive 1 unit in the y direction, and here's a point, 1, 1. Okay, that's what my absolute value function looks like. Now we knew that already. That was what we did in our last example prior to looking at piecewise functions. But this is our first example looking at piecewise functions, and I'm not done with it yet. We got the graph f of x equals absolute value of x. But I'm not quite done with this yet. I'll leave the graph up there for a little bit, but I want to do an example. Let's look and see how this works. I want to compute f evaluated at 3. So that's the absolute value of 3. And we know what we should come out with. We know how the absolute value function works. But let's just use this definition. This definition says if x is greater than or equal to 0, and we want the absolute value of x, then the absolute value of x is just x itself. Here's our x. It's greater than or equal to 0. So the absolute value of this x is going to be x itself, where the absolute value of 3 is going to be 3 itself. No problem there. This one's going to be a little bit trickier. We want f equals, we want f evaluated at -2. So that's the absolute value of -2. And notice that here, x is -2. X is less than 0 here. So this is the rule that applies. It says if x is less than 0, and we want the absolute value of x, then take x and multiply it by -1. That's what it says. Here's our x. It's less than 0. We want the absolute value of x. And this rule for x less than 0 says, if we want the absolute value of x, then we take x, which is -2, we take x, and we multiply it by -1. And we get 2. You see how that worked? Let's do another piecewise function, okay? Here's a great example. This is a piecewise function, and the definition changes at x equals 0. There's a definition for f of x when x is less than 0. There's a definition for f of x when x equals 0. And there's a definition for f of x when x is greater than 0. We're going to graph this baby. And right here at x equals 0, which incidentally is another name for the y-axis. At x equals 0, this is where things really get interesting. For x less than 0, f of x equals x squared. And we remember what the graph of f of x equals x squared looks like? Whoops, whoops, whoops. This is what the graph of f of x equals x squared looks like. And for x less than 0, where is x less than 0? Or said another way, where is x negative? X is negative over here, isn't it? X is negative to the left of the y-axis. And to the left of the y-axis, we have, let's say, f of x equals x squared. And it goes through the point negative 1, 1. Now right here, I'm going to put an open spot here because this definition for f of x is only valid when x is less than 0. It doesn't apply when x is equal to 0, so we'll have to look at that separately. But when x is less than 0, that is to the left of the y-axis, this is what the graph looks like. Now, I'm using an open circle here, at least temporarily, to show that at the origin, I'm not sure yet whether this is actually a point on the graph. What is the y value, or the f of x value, when x is 0? Here it says when x is 0, y equals f of x is 2. Ooh. When x is 0, f of x, the y value, is 2. So here's a point on our graph. X equals 0, y equal 2. So the origin won't be a point on our graph in this case. So let's see, we have the function graph for when x is less than 0. We have the function graph for when x is equal to 0. And what about when x is greater than 0? Let's look at the graph of f of x equals x. It's a line going straight through the origin. This is what f of x equals x looks like. But our function is only defined as f of x equals x when x is positive. And where in the xy plane is x positive? Isn't x positive over here to the right of the y-axis? So to the right of the y-axis, we want the graph of f of x equals x. So we want the portion of this graph that lies to the right of the y-axis. So that's this portion right here that we want. And you know what? That's exactly what the graph of this function looks like. I'm not quite done yet. This is a great example, and I'm going to milk it for all it's worth. Give me a couple more minutes. We really need to see this example worked out thoroughly. We've done the first part. We've graphed f of x. Now, we want to compute f evaluated at -3, f evaluated at 0, and f evaluated at 2. Just for the sake of getting really comfortable working with these piecewise functions. We don't see them a lot, but we do see them. This is not like those f plus g functions I was telling you about in a previous lecture, where I said in 41 years of teaching or 42 years of teaching, I have never seen anything like this outside of pre-calculus algebra. Well, the piecewise functions are not like that. In piecewise functions, we see them in calculus quite often. In piecewise functions, we see them in probability and statistics quite often. We may not see them every day, but we might see them a couple times a week. So we want to get comfortable with them. And they're really not as mysterious as they seem. Compute f evaluated at -3. So the first thing that we have to do is figure out whether our x value falls into this category, or this category. X is -3. So is x less than 0, equal to 0, or greater than 0? X is less than 0, isn't it? So this is the rule or the definition of f of x that we're going to use. The definition that corresponds to x less than 0. And it says if x is less than 0, then f of x equals x squared. So f evaluated at -3 is going to equal -3 squared, or 9. Now let's look at this one. X is 0. Does x fall into this category, less than 0? Or this category equal 0? Or this category greater than 0? Well, this one's pretty obvious, right? X equals 0. This is going to be the rule or the definition of f of x that we use. This is the definition of f of x that corresponds to x equals 0. And it says when x equals 0, f evaluated at x is 0. So f evaluated at x when x is 0. Did I say that right? I hope I did, but maybe I didn't. This says that when x equals 0, f evaluated at x equals 2. X is 0, so f evaluated at x equals 0 is 2. And now finally this guy, x is 2. So is x less than 0? Is x equal to 0, or is x greater than 0? If x is equal to 2, x is greater than 0. So this is the definition of f of x that we use. This definition of f of x corresponds to x greater than 0. And this definition tells us when x is greater than 0, f of x equals x. So f of 2 is going to equal 2. And bravo! We've milked this example for all that it's worth. And this is where I'm going to cut this lecture off. Unlike those f plus g functions and f times g functions, which you won't see outside of pre-calculus algebra, if you take if you take calculus, you'll see these. If you take trigonometry, you'll see them. If you take probability and statistics, you'll see these things. You're not going to see them every day, but you will see them with a certain frequency. And the more we do these things, the more comfortable we get doing them. These are not the ugly monsters that they appear to be at first. These are things that we can get very, very comfortable working